Hello everyone. On behalf of Dr. Palicha, allow me to share what we have been doing at Pattaya University. Here is a quick overview of the drought variability in Thailand. You can see that throughout over the century of data, Thailand is increasingly heading into severe drought and longer drought as well. So that has been the primary source of climate extreme events for agriculture. And as we all know, and also the world's important reports have indicated that extreme weather events has been one of the most critical risks for the next decade. But forecasting and adaptation using forecast has been lacking. So I want to share a story that some of you may know, but many of you may not know, that the critical elements leading up to the success of the D-Day, which is the Normandy invasion that turned over the World War II in Europe, has been weather forecasting. The forecast itself is very important because it has to predict the precise moment of a calm enough ocean status leading up to relatively safe landing invasions. Missing that means people would die, soldiers would die unnecessarily. And if there was a delay, then they would be walking into the trap. So the window is very small and it was very uncertain at the time because, as you see from this image, at the time, during the 1940s, the only way people can make weather forecast is to do this kind of hand analysis by analyzing stations transport data transport through telegrams and mapping on the piece of paper, and to have some weather officers making hand analysis. So the forecast story concentrate on this British officer, weather officer James Stack, and this is one real image of when the surface pressure weather charts look like during the D-Day. And fast forward, today we already have enough data tracing back to see what the D-Day cyclone system looked like, but you can compare that to the earlier days with handheld analysis, which you can see just a very limited station data to interpret where the pressure gradient really is. Now, compared to the German analysis, you can see that the cyclone looks pretty much the same, but the pressure gradients are very different, which led to the wind speed and also the wave heights, which are critical for this kind of a landing operation. And the success has been set increasingly in the coming years. In this video, you can see that General James Stack was interviewed by the BBC, recounting how he made this almost impossible or impossibly accurate weather forecast back then. But my point is that it's not about accuracy, it's about uncertainty. And the story has been so well known these days that just this year there is a new movie talking about these events. And here's the trailer for you.
Captain Dr. James Stagg, here at the express request of General Eisenhower.
Do we have a date yet for the invasion zone?
D-Day is in 61 hours from now. This is the largest seaborne invasion in history. Fate of the war, thousands of lives hinge on this. I need a forecast. Churchill tells me you're the best meteorologist in the country.
Get me the latest readings from every single base within 2,000 miles of Normandy. The invasion is confirmed for Monday.
Oh, they won't like this.
We are faced with a succession of two aggressive storms.
Are you absolutely certain?
D-Day will be calm and sunny. I couldn't disagree with that more.
If D-Day is cancelled, we will lose this war.
The final decision on the timing of D-Day will be mine, and mine alone.
If you invade tomorrow, they're going to be washed away.
300,000 men with families that they may
I trust you. We must face the facts. The facts, however frightening they may be.
If we delay, the enemy will be ready and waiting. They'll slaughter every single last one of us.
The storms that I'm talking about are real, and the wrath of nature is real.
Alright. Today, you can easily get weather forecasts from your phone, and they are incredibly accurate and convenient, especially for the next 3 days up to 5 days. But technology has evolved, yet it doesn't mean that human fear about uncertainty has evolved either. So as you can see from the video, there are two things the movie tries to convey. First one is uncertainty. The second thing is responsibility. Now the general said that the decision is mine and mine alone. That's a very wise decision. That's something that in modern bureaucracy, government, it's grossly lacking. The lack of responsibility of making decisions under uncertainty has been the delay of many critical operations. Just for that reason alone, I personally have written a Bangkok Post opinion talking about why the flood warning came too late for Pattaya. And as many of you know, that the forecast, let it be hydrological forecast, weather forecast, even climate forecast for the very wet, very rainy December was actually available. Even the warning and the messages about the impending flood was available, but no action was taken. So I think that's more important than technology. It's about channeling of technology. So let me bring you back further back to the beginning of World War I. So way before today's weather forecasting is made computerized and available anywhere, weather forecast was almost impossible, was not even considered a science. And all of the modernization traced back to this guy, Richardson, Louis Fry Richardson. What he did is that at the time, during the early 1900s, he published a book in 1922. He believed that by applying the physical equations, solving partial differential equations, basically predicting and calculating flux of all the meteorological elements, you can make weather prediction. His own exercise was to divide Europe into this very big grid using available station data.
Louis Fry Richardson was.
Skip that. But then he faced a tremendous obstacle. That is, to produce 6 hours of forecast, he will need 64,000 human computers, men and women, doing all the calculations simultaneously in order to beat the 6 hour time frame. Because, as you know, there's no point making a 6 hour forecast 24 hours later. And all this, at the time of his publications, has become a joke, practically a joke. The media actually mocked him because people don't see how this could be possible. And even some attempts to try to compute the real forecast, as you can see from these factory-like calculations representing each grid point of the weather map, did not succeed. The error was enormous. Until in 1945, the US Army has founded this ENIAC numerical integrator and computer, which you can see in this room. It's probably as big as this room you're sitting in, and it took a lot of energy with the capacity almost less than a handheld computer you have today. But using the ENIAC machine, scientists were able to compute the actual real forecast in time that can predict weather reasonably well 10 days ahead. Okay, for the next 10 days, within 24 hours. And these are the scientists who made it happen. And 6 years later, in today's weather forecast, now you can see a lot of very cool stuff, including something like winds, humidity, anything you can think of actually. And then they can do that globally at a relatively high resolution and continuously for the next 14 days, even longer. Now, that doesn't mean that we can make decisions easy, right? As we said, sometimes, I just feel like history is quite brutal, because even if you had the greatest idea and improve your concept, you just have to wait until technology catch up. So, for Southeast Asia, where weather observations are not widespread, I feel like there has been a lack of utilization of the modern reanalysis data. Because of the invention of the numerical weather prediction models, now people can make relatively well data, global coverage data, based upon observations, and this is how they make these observations, right? Every point in time, you have observations, and then you have forecast. Now the forecast will drift, as you know, but at each forecast time or initialization time, you can use the observations to correct it. Then you make a relatively persistent forecast. Then you use this corrected forecast, which they call data assimilation process, to make observational data. So here we come to Thailand's one of Thailand's most important crops, the cassava. And cassava was widespread and is generally low maintenance, and it's rain-fed, meaning its maintenance is low cost and potentially high yield. So that's why it made it to an important crop here. To grow cassava, usually you grow it on the open field, and normally farmers don't have irrigation, or they have very rudimentary irrigations, which means climate and weather information is very important. And we have found out that despite rainfall being important conditions, soil moisture is even more important, especially when it comes to predictions, because as you know that soil moisture can filter out the high frequency noise of precipitation. And if you look at this map, you can see that in the higher latitude regions, in higher latitudes, weather systems come in waves and they propagate. That means it's more predictable, they are more organized, and they move in one direction. Over Thailand or over Southeast Asia, you can see that the precipitation is like the popcorns. They pop up when it's moist. You can never predict when and where the rainfall is going to drop, even though the coming week will have some sort of rainfall. So using soil moisture data, don't ask me where the soil moisture data come from. That's actually why I want to emphasize reanalysis data. But if you look at this map, this time series, the red line is cassava yield, and the blue line is soil moisture over the growing area. You can just see how close they track each other. And more importantly, the soil moisture data here has an average 6 months lead time ahead of the yield, which means by using observation alone, you can have about 3 to 6 months of forecasting, predicting power. So that's the power of a broad scale cassava yield. And we also found that cassava yield can track Central Pacific, tropical Pacific Ocean temperatures quite well. And the reason is that as the large ocean temperatures change, Some people may know this is related to the El Nino or La Nina phenomenon that affect the global agriculture, and then it can shift the circulation patterns, and in this case, if it can dry up, or if it's in inverse, it can produce more rain in Southeast Asia continents. Using such knowledge and also the modern climate forecast data set, we published a paper earlier on with Kasesa University teachers about Thailand's palm oil yield using advanced seasonal predictions. And this is a proof of concept. Now back to cassava yield. Later on, I tried to use the longer governmental data, even though people may criticize it as less accurate, but it's a larger scale. Now in 2023, there was a drought which caused the cassava yield to drop about 20%. It's a big drop. And using machine learning, and factor in all those climate informations, eventually I found that using the neural network model can predict the drop 6 months ahead using ocean heat content and soil moisture, and at different lead times. And then the most important thing is how can we use this kind of information? Now, assuming that if either you are grower or processors, if you can foresee the 20% drop 6 months ahead, there are many different ways you can implement to secure your profit. Okay, that gives you an edge. Now, some of you doing cassava may have seen this report. This is a very popular report in Thailand. Every year they launch this report showing you the cassava yield in Thailand, and they also did a forecast. Now you can see that we can track back every year to see how good it is by looking at the data against the forecast. Some years it's very good, some years it's not good. Most of the time, actually, it's not good. So it's about 30% accuracy. Okay. Then, but the question comes in: how do such organizations make predictions? Right? What were they based on? Of course, they factor in many macro, economical, and agricultural data, but they also look at ocean conditions. So in this report, they never failed to implement, to show this oceanic Nino index, which means El Nino thing. So the cassava community are monitoring the El Nino conditions and using them to see, okay, we have an El Nino and what that means for Thailand's cassava yield directly. Okay, but this is a very rudimentary concept. It is more of a notion than actual knowledge. And the reason is that the monsoon of Asia, they come in phases, and they also are not just precipitation. You have to consider the circulations, and then the circulation brings moisture, and then they also evolve. They move north and south, they move east and west, and they are significantly influenced by ocean temperature changes, which will feed back to make your monsoon life cycles more stronger or weaker, or even amplify all the phases. That's the source of extreme events. Now, increasingly, especially during the pre-monsoon, even post-monsoon seasons, we have found out that the increasingly wavy middle latitude jet streams can interact with the monsoon moisture, and that's the source of occasional out of the season big thunderstorms, rainstorms that can cause severe damage. They can wipe out your entire growing season efforts by flooding it away or doing something more damaging. So in the face of drought increasing in Thailand, there has been also an increase in precipitation events. Now, if you study climate change and meteorology, you understand why. That's because the warming air holds more moisture, so it can evaporate more, but when it rains, it also rains more. So in southern Thailand, we have found an increase in precipitation, but that's not the most important thing. the more important thing is that traditionally it has associated with ENSO, but increasingly it's less so, which means it's becoming more unpredictable if we only follow ENSO. And using tree data, we have also found out that Thailand, even though it's experiencing more and more drought, longer drought, it also is showing some of the flood events, but the frequency is decreasing. It's the extreme dry events that has increased. Now you can see that this trend has only occurred post the 1970s. So the signals only beginning to show. I'll skip this part. This is classic climate diagnostics. But when we apply to agriculture here, you can see like rainfall is very scattered. So you also don't see many stations. Basically, you don't see any stations if you go to the rural areas. So how can we factor in and apply weather data? How nice if we can data everywhere for any time. And that's when the reanalysis data come into play. Now, some of the audience already know the reanalysis. For those of you who don't know what that is, I'm showing you here a 1985 study demonstrating what data assimilation can do. Now, this is the African continent. Now, you can see there's no stations. But through the data assimilation process, which means statistics, but also physical interpretation of the weather, you can now see that there is a cyclone in the middle of Sahara Desert where there's no data. How do you know it's true? Well, in that study, they show you a satellite image that shows a dust storm there. Now, this was 1985. Today, all of the reanalysis data factor in satellite data already, remote sensing data of many different kinds, which means it's more accurate. So we try to produce data for Thailand, hopefully for the Southeast Asian continent as well, at fine resolution and provide all the possible agriculturally important data sets. Some of you know the term downscaling, and the ERA5 has recently launched an agricultural data set too that we can provide to users with usage. But then we found out something more important, which relate to what I said in the beginning. How do you disseminate information? Not many people need numerical data or fancy graph. They just want information. That's why we try to establish the Kasesa University KU Center for Climate Intelligence. You can call it KUCI. The goal is not only to store and provide data, but to provide them in a way that makes sense. Now, here's a quick example how we connect all the climate data, the reanalysis data, with diagnostics, with prediction modeling to try to forecast the yield of cassava farms in northeast area. Okay, now this is just one figure showing you, some figures showing you how we did it. Now, this figure, for example, shows you different farms' historical yield of cassava. Now, sometimes in a normal year, climatically normal, you don't see much signal, you see a lot of noise. But sometimes when drought happens, like here, that's when we try to model it and can predict in advance. Because even though some farm may lose value in a normal year, well, some other farms will gain it. So in a macro scale, larger scale point of view, they end up equilibrium. But years like this, mostly dry or heat events, that's the one that produce the most damage. So we try to develop LLM or AI models. Think of it like a ChatGPT, but with a specific database for models and knowledge that we can try to use common language that can service a different array of users. This is just one example. You can forecast the coming season's cassava yield for a certain province, then it give you all the information, and it's also factor in all the climate forecast and also weather forecast. So that's the part I want to share with you today, and I hope to contribute to these programs you guys are leading. Thank you.